All right. Assalamualaikum and a very good day, everyone. And currently we are in the week 5. All right. So for Can F1023 Engineering Mathematics 2, we're still in the first order ordinary differential equation. And for today's session, I would like to discuss on the application of ordinary differential equation, still in the first order ordinary ODE. All right, so application is really important to see how uh, this differential equation work in real life. Somehow that is the goal of mathematics, is to get it to apply to things. All right. And then in this session, we will focus on being able to apply the differential equation method, uh, specifically on separable equation, linear equation, and we gonna use this method of solution what we have learned in the previous session. The method of solution for the first order ODE, there is 4 methods we have learned on the separable equation, linear equation, exact and non-exact equation, and substitution method. So we're gonna use this and we're gonna apply it, okay, of ODE for, and we're gonna find out that uh, how we're gonna apply it in the real problem in the real life. Okay. All right. So this is from the chapter 2, 3, and 4. We have identified this method by solving this uh, differential equation using this type of method. And then in this session, by using this method, we can solve linear and non-linear differential equation that common appear in uh, engineering in application. All right. Okay. We can divide uh, linear and non-linear models here. So for this week, we will focus on the linear models, whereas there is a linear such as a growth and decay, the rate of growth for a certain population, for example, bacteria or human or animals like a rabbit or whatsoever. The one is we calculate the rate of growth for certain population, and decay usually we consider on the radioactive decay, radioactive substances. All right. And then when you learn about the growth, uh, automatically you will know how to apply it for the decay part. Okay, for the radioactive substances, because it just the theoretical is similar. It's just the difference of the uh, positive and negative value for the exponential growth. Of course, it is a positive, and for exponential decay, it is a negative sign that involved, right? And then first order differential equation, we also consider on the half-life, whereas we measure stability of radioactive substances. So that one we consider is decay as well. All right. So the half-life, it's almost similar on the decay, right? So we are using the exponential decay as well, but then we consider it's a half-life of the radioactive substances. So I'll focus on the growth and decay, and then half-life, carbon dating by using radioactive carbon to determine the fossil age, and the Newton law of cooling or warming. So this thing is similar like the growth and decay, right? And then I already cover the growth and decay part, and for the other part, you just go through it, okay? You go through it by looking at the textbook, or you can learn it by your own, whereas the idea or the basic concept is similar with the growth and decay. Okay, and then the second I will cover on the mixture of flow. So this is quite important. As a civil engineer, we are dealing with this mixture of flow, uh, for the application of the mixture of flow. And then as well, we cover on the series of circuits. Okay, so these three linear models that I will cover in this session, um, in this week, within this week, right? So for the nonlinear model, there is a population dynamic and chemical reaction. So this one um, we will cover in the next session. Okay. Okay, application of first ODE. So for the growth and decay. So mathematical model for growth and decay can be represented by the initial value problem. Have you remember what is initial value problem? Initial value problem means that you are given, okay, you are given the value for the initial. Let's say in the case of growth and decay, right? So we are given the initial value of let's say this is t naught or x naught. We are given the initial value. So for the growth and decay, this is the formula that you're gonna face it every time you do the you try to solve the growth and decay problem. So this formula is we can say is standard, right? So you can use it, but it depends. Some we just change the variable, the dependent variable, instead of dx. Maybe you can, for the population, maybe you can use a dp over dt. But here as well, you can, when you change it to dp is equal to kp, right? So the t here is uh represent the time, right? So in this formula or equation here, dx dt is rate of change. Okay, dx dt here is rate of change of growth and decay. It is based on the independent variable. It is based on the time. Okay, the growth and decay of a certain thing like a bacteria, for example, is depends on the time. It's based on the time. All right, the bacteria growth or change, it based on the time. All right, so k here is a constant, whereas I can say that dx dt is proportional to the amount of growth. It's a proportional, okay, because it's equal to kx here. then we go to the point number 2 here, rate of growth. Okay, rate of growth of certain population. This one you focus on population. Okay, so the rate of growth for a certain population over short periods of time is proportional to the population present at time t. So that means proportional is when the population increase. So of course the rate of growth is or the rate of growth is increased. So this is the meaning of this sentence here. Okay, uh, it depends on the time. It based on the time, but population will increase if the the rate and growth is increased as well. Right. So if we know the population at time t naught, so usually we are know. This is in the real life you are know the t naught, the initial time. Let's say you start on 2020, so the initial of time, your time is 2020, right? So that one is initial. You start with 0, for example. Okay, so we can use the model above to predict the population in the future. So we can predict, let's say this person, this woman here, one of the women, we call it uh, A, right? So this A married and she get a son on 2020. So maybe we can predict the population for the future. So maybe we can predict how many kids that, how many child that this woman can get the birth. Uh, Maybe within the 6 or 5 years. It depends on if this woman is control taking the birth control. It depends. So well, for the population, usually we consider on the animals because for sure animals is not taking any birth control. Yeah. So for example, rabbit. Okay. So rabbit on 2020, this rabbit have uh, five babies, right? Let's say, and then 2025, within the 5 year time frame, we can predict how much is this rabbit can produce every year. How 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 is the growth, the population of this rabbit growth every year, every after 5 years. All right, this is how we're going to apply the ODE. We want to predict the population in the future. That's why this is time based. That means the population, it depends on the time. Okay. Well, we go to the next slide first. Okay, before we go to the example here, okay, we go to the basic idea or the concept of the population. Okay, so in the formula previously, we have, let's say this is for the population, we have dp over dt is equal to kp, right? So dp dt here is proportional to the amount of people that are here. So p here is a population. You can say where is a consider of the people, or in this example is the bacteria, or we consider the animals like rabbit or cat or whatsoever, right? So this from this formula here, what you can do actually by looking at this formula, because we have learned previously on the uh, on the method to solve. So from this a formula given here, I can say that I can solve this kind of equation by using separable method or linear method. Am I right? Okay. So it depends on how you choose to solve your problem. So in this case, I prefer to choose it by using separable method because I think separable is quite easy compared to the rest. But it depends on how you familiar with the method of solution. Okay, it can also can also solve by using linear equation. So it's not wrong as long as you can solve the equation. So in this case here, so this is the idea. We don't we're not going to the example yet, but this is the idea. So how you gonna derive, how you gonna apply the separable method uh, in this example later on. So we are given this formula here. Okay, what you can do next is when you do a separable method, you have to separate the variable. So the constant will remain here on the right hand side. Okay, here is the p. Okay, you can separate it. The left hand side is uh, the p variable, while the right hand side is the t variable. And then after you separate it, you have to what you need to do is to integrate it. Okay, when you integrate 1 over p, you can get ln p equal integrate k kt plus c. So c here is constant, and then you do the exponential ln p equal to e kt plus c. So here you get p e kt dot ec. Usually I do it this way, a equal to ec, because I want to consider only one constant. So p equal to a e kt. All right. So this is when we consider p at population at time. So we consider a e k sorry k t. All right. Let's say we consider for the initial t. So that means t equal to 0. Okay. So p 0. Let's say a is constant ae. So ae0 is equal to 1. So that means p when p is 0, p sub naught p p naught here is equal to constant a. All right. So when p naught is equal to constant a, we can solve this equation here, right? pt equal to p naught, okay, e kt. So this is the equation that uh, you will find after you derive it from this formula that is given in the previous slide, whereas the population of grow is proportional to the k dot p, proportional to the p population. Right, k here is a constant. Okay, well, from here, if k is positive, we can consider it as exponential growth. Okay, when k is negative, it is exponential decay. Okay, all right. So in how we gonna solve this? How we gonna apply in this kind of a problem. So for the first step, if we are given this, after we've derived, we are given this equation here. The first step, what you need to do is to find the information related to K. Okay, usually P naught is given, so T is given. So you have to find the constant K here. This is the first step. Okay, step 1, find K. So you are given information to solve the K. Usually this is the trend of the problem, and then you have to solve the K. That one is the first step. So for the second step, you are given the information to solve the question. So let's say you are given, after you find K, you have to solve the question. Okay, let's say you are given if T is equal to 5 years later on, and say how 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 you determine the population. Okay, usually that is the uh, kind of problem that is given. But maybe you are given the K value, but then you have to find uh, times. So it depends on uh, we how we how you find the problem. Okay. Um, well, can we go to this example to make it clearer for you, so that we can proceed? So before we proceed, I have to erase all of this first. I have to erase this. Okay. All right. We go to the example 1 here. So a culture initially has P naught. Okay. A culture here means the bacteria. We culture the bacteria, right? Usually we culture the bacteria. We have a P naught number of bacteria. At T 1 hour, the number of bacteria is measured to be 3/2 P naught. So that means when T is equal to 1, uh, the number of bacteria is 3/2 P naught. Okay, when T is 0, consider is P naught. Okay, if the rate of growth is proportional to the number of bacteria, okay, at time T, so we know it when it's proportional, consider is dP over dt equal to kp, because this is the proportional. Okay, determine the time necessary for the number of bacteria to triple. So that means this question wants you to find the time. Okay, first of all, you have to derive. So previously we learned how to derive. I give you uh, I give you the idea how to derive. So in this example, we just straightforward. Whereas after we derive, previously we get this kind of equation. Okay. Whereas P naught is the number of bacteria when T is equal to 0. Okay. And then after 1 hour, so we consider here, because this is the value that is given after 1 hour. Okay, what happened is P naught E K T, E K T is equal to 1 as well. Okay, and then after 1 hour, what happened is when the P here is increased to 3/2 P naught. equal to P naught EK. Alright, because it is measure is a 3 over 2 P naught. So we cancel out P naught with times P naught here. Okay, we cancel out the P naught. We divide by the P naught. What we get is 3 over 2 equal to e to the k. Alright, and then what you're gonna find next is you do the ln 3 over 2. Okay, so here e ln k is k. So k is equal to ln 3 over 2 or 0.4055. Well, this is the equation that we get. So E 0.4055t, or if you don't want to what to use this because it's too long, you can just put it here and then 3 over 2t. So this one I will consider this one as well. Okay, and then so we find this is the first step that I have taught previously. So I told you to find the k. We find the k, and then we go to the uh, we're going to solve the question. The question here want us to determine the time. Okay, we want t here. So how we're gonna do this is by, so this is the equation, not e 3 over 2t. So this is the equation that we derive. Okay, and then we want the number of bacteria. Okay, number of bacteria to triple. So that means pt here is 3. We want triple times p naught. P naught is the initial value of the number of bacteria. So we want it to be triple. So we just plug in 3 there, and then cancel out p naught here. We get here 3 e uh, e ln 3 over 2t. Okay, we just plug in number 3 inside here, and then we cancel out e here. So ln 3 is equal to this one. I just use this. Okay, so we get t is equal to ln 3 over divide by 0.455 here, which is give us the answer of 2.71 hour, or approximately 3 hour. So after 3 hour, okay, after 3 hour, the number of the bacteria is triple. So that means t here is 3 hours. So the final answer that the question 1 is after 3 hours, the number of bacteria is triple. So this is how we gonna solve this kind of problem. I think this is still easy for us to solve this kind of problem for the growth and decay. All right. So next. So okay, this is where you can use linear equation method, all right, to find uh, to find to solve the the problem, the example 1 problem. But this case you use the uh, linear equation method. All right, you can go through how we are using linear equation method by using the integrating factor e to negative k and t here. So I think this is the the other solution method that you can use. All right, so at t is equal to 0, where p is equal to p naught, thus p naught is equal to constant, so we can get this equation. All right, so this is the equation that we have derived, and then we substitute the equation to find where is after 1 hour 3/2 population is increased. So this is the way how we get the k value, right? So we get the k value here, and then we substitute back um, in the uh, in the equation. So after you find this equation, then you can solve the problem. So in the problem you have to determine the time when the number of bacteria triples. So when the number of bacteria triples, so this is how you plug in the inside the equation that we have been derived. Okay, and then you can get the time. So that means after 3 hour, let's say approximately after 3 hour, you can get the bacteria to be triple. The growth of bacteria is triple. Okay. All right. So this is exercise number 1. So for the exercise number 1 is quite similar with our example. I think it's easy for you to solve it, and I've given the answer as well. So you try it by yourself. So for example number B, 1B here is the radioactive substances. This is related to the decay. And then for the half-life, okay, you go through. This is how you self-directed learning. You have the basic idea of the growth and decay, and you go through this. You try to solve this type of um, problem, right? And then I give you the answer and you can compare your answer with my answer. Okay, so the idea is similar, just the radioactive. Yeah, you try to solve it first, and then you can get the answer same like mine, right? So we have done for the first application for the growth and decay, right? Okay, next part we will discuss on the mixings mixings of the application for the mixing. Right. Okay, guys. Hello, guys. Welcome back. So we now move into one of the main application of differential equation. So we are modeling of first order ODEs. We modeling the process of writing differential equation to describe most of the physical situation. All right. So previously we have looked at the growth and decay problems, and also the population. And now we will focus on the mixtures or mixing problem. So let's get started. Okay. So in this problem, uh, we will start with a substance that is dissolved in a liquid. Uh, liquid will liquid will be entering here. Okay, so you see here, liquid will be entering and entering and leaving the tank. All right, so a liquid will be enter here and leaving it here. Right, the liquid entering the tank. Okay, when the liquid entering the tank might or might not contain more of the substance dissolved in it. Okay, a liquid leaving the tank will of course contain the substance that dissolve in this tank here, right? So what I can say here, if you're given a tank, we consider the liquid that enter the tank. It's either have a lower or equal or higher substance that dissolve. It's we can control it. Okay, but then when the liquid that leaving the tank is of course it will mix with the liquid that inside this tank, right? And then it will mix and we cannot control the outcomes, the concentration, the liquid leaving the tank. All right, and this is the meaning of this sentence here. Okay. So we will learn about this mixing problem, how the uh, substance or how the liquid entering the tank and leaving the tank, what are we uh, considering in this problem. So if we are given the amount of substances dissolved in the liquid in the tank at any given any time, right? So if you are given the amount of substances, so we are considering the substance that is dissolved in liquid. Let's say we pick one of a substance which is salt. Okay, so let's say salt uh, is the substance, the amount of salt that dissolve in the liquid in the tank at given at any time, and then we want to develop DE. Okay, we want to develop a differential equation, and when we solve we will have an expression for that particular amount of substance, and we assume that the concentration of the salt in the liquid uniform throughout the tank. Okay. Okay, let's say we are, if we are given, okay, so we start to develop the equation here. So let's say we are given yt here, right? Yt is the amount of the substance dissolved, the amount of salt that dissolve in the liquid in the tank here, right? Yt is amount of the salt or substance, okay, dissolve in the tank at any time. Okay, t here stat at any time. So we want to develop a differential equation. So yt is here. So we want to develop a differential equation that when we solve, we will have an expression of this yt. So we assume that the concentration of the salt in the liquid uniform throughout the tank. So we assume it's fully dissolved uniformly throughout this tank. Okay, the main equation that involved in this model is dy dt, whereas the rate we can consider is the rate of liquid. Okay, rate of liquid entering. Okay, the rate of liquid R, rate of liquid enter the entering. So this is the input. So we can consider Ri here. So rate of liquid that entering the tank is minus rate of liquid leaving the tank. So Ri minus, so the rate leaving, we consider R out. Okay, so R out. So this is the main equation that involved in this model. When we consider the rate of change of yt, which is dy over dt here, the rate of change of yt, which is dy is over dt, is equal the rate of liquid entering, okay, entering the tank Ri, then minus the rate of liquid that is leaving the tank, which is R out, and this is the concept in this application. The rate here means the flow rate times by concentration. This you will learn in the example to make you get a clear view of it. But before we go to the example, I would like to share with you the concept or this idea of mixing problem. This is from one of YouTube channels that I find it's really helpful. It's really helpful for you to get a clear understanding on the idea how the this problem is, how we're gonna derive differential equation of this kind of problem, which is mixing problem, right? We go to the next slide and watch for the video and can the understanding from the video, and then only we go to the example. Okay.
When you study a certain kind of differential equation, for example, a first-order linear differential equation, it's often helpful to have in mind a physical system which would be modeled by that differential equation. So I'll introduce now a model for a mixing process, and this mixing process will be modeled by a first-order linear differential equation. So suppose that I have a tank full of salty water. I'll call it brine. Now into the tank is flowing more brine, and depending on the problem, it might be saltier or less salty or the same saltiness. Now out of the tank is pouring a perfect mixture of what's in the tank already and what's pouring into the tank. Now let's quantify all of these things. So let's say that the brine flows into the tank at a rate of R in, and it has a concentration, a salt concentration of C in. And the brine flows out of the tank at a rate of R out, and it has a concentration of C out. Let's give names to two more quantities. Let's call X of t the amount of dissolved salt in the tank, so the total amount of salt dissolved in this brine, and let's call V of t the total volume of the brine. Now these two quantities are changing in time. V of t, for instance, may be changing if the rate in is different from the rate out. And X of t will of course be changing because mixed brine is flowing out. Meanwhile, other brine, maybe saltier or maybe less salty, is flowing in. So the total quantity of salt in the tank will be changing. Our model will be a model for the amount x of t of dissolved salt in the tank, and we will find that it is a first-order linear differential equation for x. Now, how could we come up with such a model? Well, let's consider a small time interval, delta t, and let's try to write down what the total change in the amount of salt is over that small time interval, and let's call that delta x. So, well, what is delta x? How does the amount of salt change over a tiny time interval, delta t? Well, in a tiny time interval, a certain amount of salt flows in, and a certain amount of salt flows out. And it's not too hard to deduce that the total change in the amount of salt will simply be the amount that flowed in minus the amount that flowed out. Now, how do we determine how much flows in and how much flows out? Well, we know the rate at which brine flows in, and we know the concentration of salt in that brine. Knowing these two quantities, we actually know the rate at which the salt flows in. It's C in times R in. For example, if the rate in is 1 gallon per minute and the concentration in is 1 gram per gallon, then the rate at which salt flows in is C in times R in, which is 1 gram per minute. So same goes for out, the rate out. So the rate of salt flowing out is C out times R out. So we know the rate at which salt flows in, and we know the rate at which salt flows out. So how do we figure out the total amount of salt that flowed in and the total amount that flowed out over the time interval delta t? Well, we multiply by delta t. So the total amount of salt that flows in over that small time interval delta t is C in times R in times delta t. And we subtract the total amount that flowed out during that time interval, which is C out times R out times delta t. Now, this is not yet a differential equation, but we're considering a little tiny time interval delta t. So we can turn it into a differential equation by dividing both sides by delta t and letting delta t go to 0, so taking the limit as delta t goes to 0. So that quantity delta x divided by delta t becomes dx dt, and dx dt is equal to C in times Rn minus C out times R out. Now, what we've got here looks pretty good, but it doesn't look like a differential equation yet. On the left-hand side, I have dx dt, and on the right-hand side, I have these funny things, C in, R in, C out, R out. So let's see if we can make this look like a differential equation. And to do that, let's consider the following question. What quantities on the right-hand side do you control, and which do you not control? So let me explain what I mean. Suppose that before we begin to conduct this mixing experiment, we mix up a bucket of brine off to the side ahead of time. And that's the brine that I'm going to pour into the tank. So by mixing it ahead of time, I got to control the concentration in. I get to control C in. And by pouring it into the tank, I got to control R in. On the other hand, maybe I can open and close the valve for this drain pipe going out. So maybe I get to control R out. On the other hand, I have no control whatsoever over C out. C out is determined purely by the quantity of salt in the tank and the volume of the brine in the tank. And how do you determine that? Well, you want to know what the concentration out is, so you divide the total amount of salt by the total volume. That gives you the amount of salt per unit of volume, x of t over v of t. Now, that's exactly the kind of thing we're looking for. We want to incorporate x into this right-hand side. So by plugging in C out equals x of t divided by v of t, we get an ordinary differential equation for x of t. And that is dx dt equals C in times R in minus R out times x of t over v of t. Depending on the problem, we will be able to figure out what C in, R out, and v of t are. And in order to find x of t, we'll need to solve this linear first-order differential equation.
Alright guys, we go to the example. So the first statement here is we can say that this is the definition of the mixture, where we are giving the mixing of two salt solution of differing concentrations that give rise to a first order differential equation for the amount of salt content in the mixture. So this is just a, I can say that this is just a definition. Alright, so we go direct to the example here. So in this example, we are considering a large mixing tank here that hold 300 gallons of brine. Brine here is the water with dissolved salt. So we call it as a brine. We have a volume of 300 gallons of brine. Okay. And another brine solution is pumped into, right? So brine solution that is pumped into the large tank at rate here of 3 gallon per minute. So right here we can say that 3 gallon per minute. So this is rate, initial rate. So and then with salt concentration. So this one you consider is initial concentration of 2 pounds per gallon. When the solution in the tank is well stir, it is pumped out. Okay, and then it's pumped out at the same rate as the entering solution. So it's a similar. So R2 initial and R out is equal to 3 gallons. So C out here is, we don't know what is uh, the amount of the concentration of the salt that is going out. Yeah, this is not under our control. Okay. All right. Next. Uh, so if AT denotes the amount of salt measured in pounds in the tank, okay, you can consider this is AT. This is AT, amount of salt. So in this example, we are using 80 as the amount of salt that measured in pound in the tank. Okay, so 80 is the amount of salt measured in pound in the tank at T time. Then the rate of AT change is, so here we are using A here, okay, because we denotes the amount of salt as A instead of dx or dy. So it depends, okay. So as long as you know what is A here represent of what, okay. So in this case, uh, I assume dA over dt is the amount of salt uh, with respect to the time. Input rate of salt, R in, okay, minus output rate of salt, which is R out. Okay, don't get confused between the uh, small r, this one, the rate r, small r, and this is the capital letter R. So then don't get confused. Usually R I R in input rate of R is equivalent to C I, which is a concentration, initial concentration, times rate, initial rate. Okay, in this case, CI here is 2 pound per gallons. It times input initial rate here is 3 gallon over minute. So we cancel out gallons here. We get 6 pound per minute. So we get this one. Okay. How about R out? Rate out, the output rate of salt. So this one, the output rate, this is small r naught. So we want the R out is similar like C output times R naught. So we don't know the concentration of our C naught here, C out here. So how are we gonna solve this problem? Right? You go to the next slide. Okay, since the solution is being pumped out the tank at the same rate as pump in. Okay, so that means this is the statement of the question previously. So our initial is equivalent to our output, same rate. Okay, the number of gallons of brine in the tank, okay, at time t is a consistent 300 gallons. Okay, the number of gallon of brine here constant at 300 gallon. Thus, if CT, okay, if CT represent concentration of salt in the tank, okay, CT here represent the concentration of the salt in the tank here, okay, equal to AT. A, what is A previously? A here, A here means amount of salt. Okay, this is amount of salt in the tank over 300 gallons brine. So that means this is over volume here, and AT is amount of salt. Salt. Okay, and then we can get the concentration of T, which is here. CT or C output. It's either one. So I like to use this C output here. I'm so I know C in CI RI here is C not R not CO RO. Okay. So by doing it this way, we know AT here R out is equal, this is C, the concentration, right? The concentration that we want to find here is in term of pound per gallon. Okay, and then we times by 3 gallon per minute. This is our no, okay, this is given 3 gallon 3 gallon per minute. This is given in the previous in the question. So times by 3 gallons, and then you cancel out this one. What do you get is equal this one 300 3, and then this one, this is 100. So you get this A R out is equal A to A of T over 100 pound per minute. Okay, so this one is this one. Okay, so this one you get the input rate previously 6, right, 6 pound per minute, and then you minus A over 100. Okay, so this is how you get the A over dt. You understand? So that means input rate previously R in, you get R in is equal to 6 pound per minute, and now R out is equal to A over 100 pound per minute. So you just plug in side R in here minus R out here. Okay, so this is or you can arrange it in in this way. Okay, we go to the next slide. Well, this is the uh, differential equation that we have derived from this kind of problem, the mixing problem. So from this equation here, uh, you can solve if you are given if the question give you time. Let's say time is equal to 3 hour, and then you can solve it by using this equation here. Okay, so this is the I can say that this is the final answer for this type of question. Okay, so for the mixing problem. All right guys, I continue with the example. I would say it's example B because it's continuing from the uh, previous example. So I will say this is example B, right? So based on the problem that discussed in the previous slide or previous example, so if 50 pound of salt were dissolved initially in the 300 gallons, so how much salt is in the tank after a long time? So a long time here means our T is equal to infinity. Okay, infinity. All right. So well, this is the differential equation that we have been derived from the previous example, and the initial value here we are given a0 when t is equal to 0. Okay, when t is equal to 0 is equal to 50 pound, right? So the amount of salt, when the initial amount of salt is equal to 50 pound, right? Okay, and then we solve using by looking at this equation here. I know this is a linear equation method, so we have to use linear equation method by integrate, by multiply, by obtain the integrating factor. So previously, if you remember, e p to x dx. So here we consider this is our p over t, right? So our p here is 1 over 100 dt. So e, you integrate 1 over 100 dt is equal to e 1 over 100 t. Okay, right? Okay. So this is the integrating factor. Then we can solve it by using uh, the next step for linear differential equation. Okay. Okay, guys. So next is we solve this by the next step or the linear equation method that we already learned in the previous topic. Okay, so we try to solve this by using by using linear equation method, by differentiate d over dt e 1 over 100 t times a is here, okay, and then equal to the to integrate 6 is here. This is based on the formula, the step for the linear equation step previously, okay, and then e 1 over 100 t dt. So you into entire derivative here, 6 e 1 over 100 t, and then d over dt here you just bring e 1 over 100 t down here, and then this one you have to integrate 6 here, e 6 e 1 over 100, and then uh, by using by solving this is the final answer that we will get. Okay, and then uh, we are given previously the initial variable problem, okay, where um, when a t is 0 is equal to 50. So by this initial variable problem, we can get the c here. We substitute a is equal to 50. Okay, a here, sorry, a here 50, and then 600 minus c e to the 0 is 1. Okay, so 600 minus 50, you get negative, uh, it gets 550, right? Okay, and then this is how you just plug in the constant value 550 inside here, and then that's it. You solve this is a particular solution for this this method. You can, but how much salt is in the tank after a long time? So this one that I've been told that we consider t into the infinity here, and you can try to submit t is equal to 1000 minutes or 5000 minutes, but still this will give you the answer of a 6 approximately 600 pound here. Try to submit here. So this one because we consider it's a very long time, so t is equal to thousands or 5000 minutes or any value that you want to solve that is uh, that will take a very long time, right? Okay, we go to the next. And in the previous example, okay, we assume that write in is equal write out. Okay, so in this example, okay, this is another example. All right, so we consider it's either a read in is lower than read out, or read in is greater than read out. So previous example, we are given ri equal to ro, which is 3 gallon per minute. So in this example, our we will take this one, our ro is equal to 2 gallon per minute, which is our read out is smaller than our read in. So but well, the liquid accumulation in the tank will be this one, 1 gallon per minute. Then after the t minutes, okay, so after the t minutes, we times by t, and then we get the t gallons. So that means inside here, so we consider the 300 inside the tank previously, the 300 we plus by t, because t gallons of liquid that accumulate inside the tank. So this 300, okay, we plus by t, and then we can get the gallon of brine inside the tank. Okay, so um this is when the read out is lower or smaller than the read in, so we can get uh, the volume the volume of brine is higher than previous example. Okay, so this is the meaning of when we solve this kind of read out is that means slow. When we control the red the liquid going leaving the tank, so that means our volume is higher. Okay, all right, so thus if ct represent concentration of salt in the tank, So what happened to the CT? So we are given RO, which is lower than R, smaller than R in. So how about the CT? Okay, or CO here. Okay, so we know that A here is amount of salt inside the tank, and 300 plus T here is the volume of brine. Okay, this is amount of salt. This is amount of so by divide these two, we get the concentration that is that is leaving the tank. All right, and then R out is given by 2. Okay, this CT here is we divide by amount of site divide by volume. So this is the R out here. So we get the R out is 2A over 300 plus T. So automatically we get this. And this one is 6 in the previous example. Okay, because the R initial and C initial uh, is similar with the previous example, so we get 6. Okay, so we are not taking we treat this as a constant because it's similar with the amount is similar with the previous example. We raise 3 times 2 here, we can get the input rate is 6. Okay, so 6 minus the output rate, I just plug in this equation inside here. So that's it. So here is the you arrange it in the linear equation terms here. So you get dA over dt plus 2a over 300 plus t equal to 6. Okay, so that means we get different differential equation if we are given a different rate, right? So I think um, I think it's okay for now. So this is how you must understand on how we're gonna solve case by case for the mixing problem. Sometimes we are given the rate initial, which is either is equivalent with the rate rate output, or either it's greater than the rate output, or either it's lesser than the rate output. So this is how we're gonna solve this kind of problem. Okay, all right guys, so I think for at the moment, I hope that you understand how we solve this kind of differential equation of the mixing problem, right? And then I think that's it for this part. So we will continue for the series circuit later on, and let's uh, okay.